Okay, now it's recording. So let's get started. Today, we're going to discuss, something we discussed before, but not really. We only mentioned something when we study this ring structures and so on. We study the so-called homomorphism. And today, we will discuss more about the homomorphism, including some fundamental theorem of this isomorphism or homomorphism, and also the ideal, so-called ideal. The ideal is a very, very important concept on the ring theory. There is no corresponding concept or terms in the group theory. So this kind of ideal is something unique in the ring theory or the field theory. I think some of you may heard this kind of, may learn this kind of thing, this kind of ideal things before. If you try to do the bonus problem we have, then you have to know what is ideal, because you have to understand what is PID, what is UFD, what is Euclidean domain, and so on. But if you haven't, this ideal is something more or less like something that makes sense as a subset of a ring. Okay? There is actually a joke about this ideal as in ring. So this is not a good joke, but I would like to mention it to you. Someone argued that, since we are using WeChat and QQ, then why do we only have this WeChat group and the QQ group, not the WeChat ring or WeChat field? The reason is, because WeChat or the Tencent does not have an ideal. This joke, you have to understand it by translating it into Chinese, okay? So let me review what is a homomorphism for you, okay? So what is a homomorphism? Homomorphism is something, it's a map that can consist all the ring structure, okay? So let's say we have two rings, and you do want to compare the ring structure between these two rings. Then we have a map or a function. Let's say it's phi from R to S. We call it a homomorphism or a ring homomorphism. If for any AB in R, in this domain, you will have first, this phi will maps the addition to the addition, maps addition in R to the addition operation in S. Okay, and the second, it can map, moreover, the multiplication, the multiplication to multiplication. Okay. By the way, again, if you do have any questions, please unmute yourself and talk to me. Okay. And third, which is also necessary, it maps the multiplication identity to multiplication identity. Okay, so then we call it a ring homomorphism.
Do homomorphisms have to be like continuous, or it's something else?
That's a good question. But if you do want to discuss whether a map is continuous or not, you are not thinking about the algebraic structure. Okay, you are thinking about the topological structure of a set. So that's something different. They are not, the topological structure of a set and the algebraic structure of a set, they are kind of independent. But of course, if you try to study in the future the functional analysis, then you may have to study the so-called topological vector space. And then if you try to study this kind of space, the algebraic structure and the topological structure will try to talk with each other. Then the situation becomes more complicated. Okay, but at this moment, our ring homomorphism, you cannot really say whether it's continuous or not, because you don't have a topological structure on these rings. Okay. Then, well, as long as we have this homomorphism, we can try to study some subset of the rings. Okay. For instance, we know that if you have a map or a function, then you have the image, you have the domain. A domain of this set must be R. But then the image of this set is of this function is it's something like a subset of S. It's a ring homomorphism. Then we know that, okay, the image of phi is a subset of S. But moreover, since this phi is actually a ring homomorphism, it's more than a subset. It can keep the ring structure as well. So it's actually a subring, which means it's not only a subset, but also a ring, okay, of S. This means both subset and it is a ring, which means, well, basically it keeps operations, and moreover, this set is closed under the addition and multiplication, okay? Similarly, in math, when you try to think about the map, well, the image is very important. But meanwhile, another thing is also very important that you may not think this kind of thing before, but in the algebra class, you have to think it a lot, which is so-called the kernel of a map. In analysis, this is something different. So let's say we have, well, the kernel of a ring homomorphism. Well, actually, this is actually, in general, it is also true, but then you will need something like a zero element on your set. The kernel of a homomorphism is a set. The kernel of phi is a set such that, well, it maps this set to 0. This function maps every element on this kernel to 0, or which means it's more or less like a 0 set, or the set of the root of this function. So of course, in analysis or in your calculus class, the root of a function is important, right? We always try to find the root of a function, but you will find that, okay, the root of function is just some discrete set, right? You only have a several roots of this function or polynomial or something. But here, this is the difference between this algebra class and the calculus class. Here, this kernel has much more complicated structure if you have a ring homomorphism, okay? And of course, in the future, if you study geometry, then this kernel of a map is more important. Well, you will see that in the future if you want. Then for this kernel, I would say it's as important as the image. Make it slightly larger. Let me make it slightly larger. Okay. Maybe I shouldn't. I just want to make it slightly larger. Come on. Anyway, the same doesn't work. Okay, so I will write above this line. So, well, the kernel, as I said, is as important as the image of this homomorphism. The reason is, well, the kernel, well, if you're trying to study the structure of the kernel, it's actually also a subring. And it's actually a subring of R. It's actually more than that if you try to, well, study it. In analysis or in calculus, you don't really see this kind of thing. But here, if you try to study a little bit more than that, a little bit more on this ring homomorphism, you'll find that it's actually, well, has a better structure. Which is, we call it the ideal, okay? This will the kernel of a homomorphism. It has some properties, so-called, well, it is ideal. Let me give you the definition of this ideal. What do I mean for an ideal? An ideal is basically a subring of a ring, okay? So let's say R, let's say is commutative. Here, when you talk about this ideal, you will need to think about, well, some commutative ring, so that it may make life easier. Otherwise, you have to study, well, the left multiplication and right multiplication. Here, we assume it's commutative ring. And, well, then we say a non-empty set, empty subset, I in R, an ideal if it satisfies these following two conditions. I'll explain why later. First, it's closed under addition. If you have a B two element in this ideal, in this subset, then A plus B is also on this subset. Okay? It must be closed under addition. It is also closed under multiplication. However, we want a little bit more than that. That is, for any A in this set, in this subset, then for any R in your ring, if you do the multiplication R times A, it will still on this ideal I. Okay? So what's that? I mean, what do we want to define? As examples, I want you to think this kind of ideal things are more or less like something like, well, for instance, all the numbers Z, all the integers is a ring, right? Then if we want to study all the numbers that can divide 3, like this kind of thing, 3Z, okay? All the numbers on this set is a multiple of 3. Then this is an ideal. Why is that? First, if you have a multiple of 3, add another multiple of 3, then of course you still get a multiple of 3. And second, whatever number you have, you multiply some number that is a multiple of 3, then it is still a multiple of 3, right? So in some sense, this ideal is more or less like an infectious disease, right? It's like the coronavirus, right? And,
Can I ask a question?
of course.
If we're working in the real numbers, like
Mm-hmm.
if we have the second property, why do we need the first property? Because
Well, that's a good point. Well, if you try to think about if we study this z, right, then of course if you have one number on this subset, then well, addition is closed. Then of course all the multiple of this number is on this set, right? Yes, that's right. So which means if you study z, then it doesn't matter. But remember, in our course, z is just one example of ring, right? There is another very important example about ring. That is a polynomial ring, right? In a polynomial ring, if you try to study, okay, the ideal of the ring, then maybe we can, instead of the multiple of 3, you may try to study this, well, multiple of some polynomial, like this kind of x minus 2 multiply a polynomial, right? And this is also another ideal. And for this ideal, if you only have condition 1, it's not enough. You have to have the condition 2, right? Because on your ring, on this R, you may have more than integers. You may have more than integers, so that the addition is not enough. Okay? As I said, this kind of ideal stuff, this ideal, is more or less like this well, infected disease, right? If you are in this infected set, then whatever else, well, whatever somebody else it touch you, then this somebody else will also in this infected set. Okay, well, you can try to imagine is intuition of the ideal. But in real, if we try to study this ideal simply because we like to study this kind of sets, okay, like the multiple of 3 or all the polynomials that can be divided by x minus 2. Okay.
Also in set reading seminars, like set theory reading seminars, we had another definition of an ideal, and it was different, I think, right? Decoder, do you remember the definition of an ideal from set theory? Because I feel like it was like
I don't think we have a definition on set theory because this ideal is something highly related on this algebraic structure. Do we have any?
maybe it was just another like definition, but with the same name. Okay, never mind.
I think maybe it's on the chapter of the well, abstract algebra on the set theory seminar, and then maybe we discuss something about the ring. I think, but whatever. Well, whatever you remember before, you can try to double check with that, but still the ring definition will be equivalent to this one. Okay. Okay. Here are 2 examples about the ideal as a subset of a ring. It's more than a subset of a ring. And there are more examples about the ideal. For instance, well, if you have a ring, what would be the smallest ideal of this ring? Any idea? What would be the smallest element, well, smallest ideal on this ring? What do I mean by smallest?
With a list number of elements.
You can think about it like that, yes. What would be the smallest if you consider the number of elements?
Wait, on which ring is the smallest number, like the smallest ideal we're looking for?
Is it going to be like something like the smallest ideal is the subset of any other ideal?
Yes, that something makes sense, right? then what would be the smallest one? Well, the zero ideal, right? Empty set is not an ideal because we want an empty subset. Then the smallest one that satisfies this 1 and 2 would be the 0, the additive identity, right? You can see that, okay, if you only have 0, then whatever you add, you're still in this set, it's still 0. Whatever element you multiply it, it will still be on this 0 set. Okay, this is a trivial case, and we sometimes call it a zero ideal. Okay, and of course we have something else. We have this kind of ideal. There's something which is why we're interested in this ideal stuff, but we still have some ideals that can be generated by those ideals. For instance, let's say R is a commutative ring. Then let's say I1 and I2 are both ideals. Well, what we can say is the ideal, you can do an addition of these two ideals, which is, you can imagine, what is the addition of two sets? Well, the addition of two sets would be you have one element from one set and another element from the other set, and then you add them up. And all this kind of element forms the addition of two sets, right? So it's actually all the element A such that A can be written as I1 plus I2, where I1 in I1, I2 in I2. Okay? If I1 and I2 are both ideals, then I1 plus I2 is an ideal. You can check that. Why is that? Well, because first addition, of course, is closed, and then multiplication by any element on this R is also closed, right? You multiply anything, then this guy is in I1, this guy is in I2 as well, okay? Moreover, if you take the intersection of I1 and I2, it's also an ideal. Okay? I think I already know what is the definition of intersection. Then the intersection of ideals are ideals. Why is that? Okay, again, you can try to show that by multiplying something, by adding two elements on this set, and by multiplying any other thing on R on this set. You can find it's still an ideal. However, please be careful. The unit of these two ideal is not an ideal, may not be an ideal. Okay, may not be an ideal. So here, when you're trying to study the ideal, you will have to change your mind from study some set by studying some real algebraic structure. If you try to study the operations of two ideals, you can study the intersection. But then, on the contrary, you can only study the addition instead of this union of two ideals. Okay, I will change to another sheet. Okay. And as an example, of this, operations of ideals, we can think, okay, for instance, we are in Z, okay? And as we mentioned before, AZ, which is all the numbers that is multiple of Z, and BZ are both ideals. Okay? Then what we can do is we can do this operation AZ plus BZ. What it is? Well, AZ plus BZ, as we mentioned before, is all the numbers that can be written as two parts. One part is a multiple of A, another part is a multiple of B, right? So which means it's all the numbers of these four, right? What's this? What's this? I mentioned this before. What's this?
They have a greatest common divisor.
Yes. So as we mentioned before, it's actually all the multiple of GCD of AB, right? Every element on this set has a factor GCD AB. And this is actually the greatest one. So which means these two guys, these two ideals, if you add together, you will get GCD AB times C. Okay. What about we take the intersection? What happens if we take the intersection of AZ and BZ? All the numbers.
It would be the set of like the multiples.
So which means it divides A and divides B. All the number of this kind of thing, right? All the numbers such that this number divides A and divides B. So it's a least common multiplier of AB times, right? This LCM is a least common multiplier, which is the smallest number such that it divides A and divides B. Okay? Any question? And the last example of this, of this ideal is, let's say we have a ring, we have two commutative rings. And we have a homomorphism, ring homomorphism. Then we know that the kernel of this homomorphism is an ideal. It's not only a subring, but also an ideal. This is something very important. And this is actually the reason why the kernel of a homomorphism sometimes is more important than the image of the homomorphism. It's simply because the image of a homomorphism may not be an ideal, but the kernel is always an ideal. Okay? You can check this. Why this is true? Well, it's very simple because you have something, if you have A is on this kernel, then what we can conclude is any number times A is also 0, right? So second condition satisfied. First condition is of course satisfied. Okay? So this is a very important example about the ideal. And another example is something we mentioned before, but we may have a different description. That is, well, if you have one element, what you can get is you can find the smallest ideal that contains this element, which is the ideal generated by one element. For instance, you have A in R, and R is a commutative ring. And the ideal generated by A is you use any number to multiply this A. Okay? It's the smallest ideal contains A. And then you can see that this kind of ideal are actually an ideal generated by a number A or B, right? So actually on Z, the ideal generated by 3 is actually equals to 3Z. Okay? Any question? And moreover, you have this ideal generated by one element. Question? Okay. So you have this ideal generated by one element. You of course have element with ideal generated by multiple elements. A1, A2, and AN. Generated by n elements. And then, well, this is all this kind of numbers. It's R1, A1 plus R2, A2, and so on. It somehow looks like, not really, this, vector space, right? If you have a vector space, then of course you can generate it another subvector space, a subspace, by choosing some vectors and then do the linear combination. But here, be careful. What we do here, this generated operation, is something we try to do it by using element in R. In a vector space, you don't really do that because in a vector space, you don't really have this kind of multiplication operation. But in a ring, we do have this multiplication operation so that we can choose this coefficient in the ring itself. Okay, so which makes this generated ideal somehow different from this vector space, the subvector space, subspace. Okay, and any question? Okay, so of course, if you have two ideal, or if you want to find the ideal that generated by one element, for instance, the ideal generated by x minus 2, you may choose a different representative element on this ideal. For instance, this ideal is actually equals to the ideal generated by 2 times x minus 2. Okay, and the reason is simply because x minus 2 is in this 2 times x minus 2 on qx. Okay, x minus 2 is actually belongs to the this ideal generated by 2 times x minus 2 because x minus 2 is equals to 1/2 times 2 times x minus 2. Moreover, 2 times x minus 2 is in this x minus 2, right? Because 2 times x minus 2 is equals to 2 times x minus 2. Right? So that means, okay, x minus 2 and 2 times x minus 2 are the same. And moreover, if you want to check whether two ideal generated by two different elements are the same or not, you can just check whether this representative element and this representative element are the same up to a unit, right? If you multiply a unit in front of this element, then it doesn't change this ideal. Okay, you see, 2 is actually a unit on Qx. And we have this kind of thing, and then we can call this kind of ideal as a principal ideal. We say an ideal I in R is principal if you can find an element on this R such that this I is generated by this element, or H belongs to I. If, moreover, R is an integral domain, and well, we want it to be integral domain simply because we don't want the zero divisor, and otherwise this kind of ideal may somehow become trivial. And every ideal of R is principal. We say this ring principal will integral domain or PID, a principal integral domain. And well, interesting thing is, when we talk about this when we talk about this PID, the principal integral domain, there are a lot of things we have discussed a PID, which is pretty good, because that means at least in a large range of the ring we discussed, we only need to discuss about well, the principal ideal, which is the ideal that generated by one element, only one element. But of course, this may not be true. This may not be true in general. So I will switch to another piece of paper. Well, this may not be always true if you try.
Sorry, would you mind putting your paper on your second account, because I need to.
Of course, I will upload this kind of board writing for sure. Okay. So of course, not all of this ideal or principal ideal are generated by one. For instance, there is one example such that you can show that not all the ideals are principal ideal. For instance, well, let's say our ring is ZX. It's a ring, okay? And let's say the ideal we try to study is an ideal generated by two elements, 3 and x plus 2. We claim that this I generated by two elements is not an ideal. It's not a principal ideal. Okay? Why is that? Why this ideal generated by two elements is not, it cannot be generated by one element? Well, let's say, suppose this I is actually a principal ideal. Let's see what happened. Okay, Suppose I is generated by one polynomial. This is a polynomial with an integer coefficient. Okay? Then what do we have? Then we do know that 3, well, it is an element of this fx, so that means 3 can be written as some polynomial times fx, right? G is in R. So that means fx divides 3. Moreover, fx divide x plus 2. So that it can be a principal ID. Otherwise, it cannot be true, right? And then what do we have? Then that means, well, fx divides 3, that means fx of degree must be 0, right? It is not empty, so fx well, must have a degree. So fx must be a constant. And this constant, well, since it divides 3, it could be plus or minus 1 or plus minus 3. Plus or minus 1 is actually the unit. So we only need to discuss about 1 or 3. If fx is equals to 3, well, this probably cannot be true, right? If fx is equals to 3, then we must have 3 divide x plus 2. But 3, we know that it doesn't divide x plus 2. So that cannot be true. What if fx equals to 1? Fx equals to 1. What does that mean? That means this ideal is generated by 1. Okay? And is equals to 3x plus 2. By the way, what is the ideal that's generated by 1? There's one single element. What is the ideal that's generated by 1? Yes, it's actually everything, right? Remember, what is ideal? Ideal is just something that you can multiply whatever on it. If it's generated by 1, then that means you can multiply anything by 1. And then that's actually everything, right? So if it's generated by 1, if some ideal is generated by 1, then that means, okay, it's actually everything. It's a whole set. It's a whole ring. So suppose this 3, x plus 2 generate everything. What does that mean? That means there exist 2 polynomials, right? Let's say, well, hx, tx, such that tx 3 times hx plus x plus 2 times tx is equals to 1. This is a definition. 1 belongs to this this generated set. So that means you do have 2 polynomials such that this equation is true. But is that possible such that this is true? Well, if you plug in x equals to minus 2, you find that okay, 3 times h minus 2 is equals to 1. But h minus 2 must be an integer. So this is a contradiction. This cannot be true, right? So the conclusion is I is not a principal ideal. Not all the ideals are principal ideal, unfortunately. Okay? But although we know that not all the ideal are principal ideal, but still, as I said before, there are a lot of rings such that it is actually a principal ideal domain, a principal integral domain, PID. Okay? For instance, the ring we try to study a lot, that is, well, Z and Fx. the integers and the polynomial ring are PIDs. If if you learn by yourself the bonus problem chapter, then you will see that the key reason why these two are PID is simply because you are able to do the Euclidean algorithm on these two rings, because they are Euclidean domain. Then they are PID. But here, let me prove this is true. Z and Fx are both PID. Okay? Let me prove it. The proof is actually pretty easy. You can try to imagine why this is true, and it's not very hard if you try to write it down. So let's say, for instance, we try to study Z first. Let's say you have an ideal I, which is an ideal of Z. We want to show that this I is actually a principal ideal. Then we are done, right? Then every ideal, arbitrary ideal, is a principal ideal. So now we only need to say that this is an ideal such that it's actually principal. Why is that? Which generator we can find from this ideal? Any idea?
We can take one.
We can take what?
Oh, wait, are we trying to prove that Z is a PID, then we can just take one, or you mean something different?
Well, PID it means all the ideal are principal, okay? But if you try to take one, then the ideal generated by one is actually everything, right? So it cannot be this ideal. So probably this take one as a generator of this I may not be a good idea. So you see that we see some examples about ideals in Z, right? For instance, 3Z is an ideal of Z. And we know that it's generated by 3. Then, how can we find, if I gave you an ideal, how can we find this generator? How can we find this generator?
Well, we can take like a common divisor of all the terms.
But the question is, why the common divisors exist? You may have infinitely many numbers, right? Then you may check find a many, and then you find, okay, they have a common divisor. Then that might be the common divisor, but you cannot really say that it's actually a common divisor. Well, the idea is actually the same as we did before. Let's try to, because you are studying these integers. For integers, we have the best property, which is the integer set. The integer set of integer is actually well ordered, which means as long as you have a subset, you can try to find the maximum one, well, the minimum one. And it is well defined as long as you keep everything to be positive. Okay, so let's try to find an element which does exist by the well-posedness, well-orderedness. Let's say A is okay, anyway, let me put it here. Okay, let A be the smallest positive integer on I. Such A does exist. Okay, then we claim that, well, this A generated everything. It can generate everything. Okay, let's see why. First, we do know that this this principal ideal is actually a subset of I, right? Because A is in this I, so of course the ideal generated by A is in this I. Okay. Then what do we have? We have for any B in I, we want to show that B is also in this A. We want to show this. If we can show this, then we are done, because that means I is a subset of A. That means I and A, the ideal generated by A, are the same. Right? But then how can we show that B is actually in A?
If B is not in A, then we can expand it. Then there is a remainder, and you can claim that the remainder is smaller than A, and there's a contradiction.
Great. We can do this Euclidean algorithm. We can try to write this algorithm if B is not in A, or B is not a multiple of A, right? What is ideal generated by A? It's just A times Z, right? It consists of everything that is a multiple of A. If B is not in A, that means B can be written as AQ plus R with R greater than 0, less than A. But we do know that R is also in this ideal, because B is in this ideal, A is in this ideal, so that B minus AQ is also in this ideal. R is smaller than A, which is a contradiction. Okay? So this is why B must in A, or A is actually in equals to.
Oh, wait, sorry. I kind of, so basically the property of ideal is that we have the summation and we have like if we multiply by some number from the ring, right? But
Yes.
here we do not the summation, we do like subtraction.
Because
like,
minus 1 is in this, minus Q.
oh, wait, because we're working with all integers.
We are
not
working
just
on Z.
one.
Remember,
yeah,
we are
yeah.
working on Z. Of course, if you try to study the general ideal, if you do have a Q in this ideal, then the additive inverse is also on this ideal. You can show that. Okay? Okay, so we have this Z is actually a PID. The same, well, the proof for fx is a PID, it's the same. Okay, which means whatever you have, as long as you have a field, then this fx is always a PID. Okay, any other question? If no, then I will change to another sheet. So this is actually pretty good, because that means, okay, if you try to study the ideal of Z or fx, you only need to study the principal ideal. Okay? Then what we have is, well, something we can study. For instance, we can study the so-called splitting field, or something like you add some root to a ring to fx. You add some root of a polynomial to f. Then you just need to try to study this fx, well, the domain of some fx, well, the ideal of some fx. Well, if I is an ideal, then you find one prime number on this ideal, then this ideal must be able to write it as the ideal generated by this prime number. Similarly, if you have some ideal that is not everything for fx, you find one polynomial on this fx, and fx is irreducible prime number and irreducible polynomial. If you find something irreducible, then this ideal is generated by this element. Okay? So which means if you're trying to find an irreducible polynomial, then you actually trying to find this principal ideal. And moreover, let's say f in capital F is irreducible.
Oh, sorry, a question. So our proposition last time was that fx is also a PID, right? But we cannot use the same proof because we kind of can have the smallest polynomial, or you mean?
We cannot have the smallest polynomial, that's true. But do you remember when we try to prove this Euclidean algorithm of a polynomial, what substitution we have? We don't have the smallest number for polynomial, right? But what do we have? When you're trying to use a mathematical induction on this Euclidean algorithm.
Guys, help.
Well, anybody knows? What do we have when we try to use well, the mathematical induction to prove something for polynomial? If we try to use the mathematical induction to prove something about the integer.
Oh, we can use a degree, right?
Yes, we try to study the degree of polynomials, right? And we don't have the smallest number, of course, but what we do have is the smallest degree of polynomials. Up to the unit, it is unique, right? So this is something we can use. If you try to do this kind of algorithm, like what we did for this integers, we try to run this Euclidean algorithm, right? Similarly, for polynomial, you can do the same thing, but not really like this, but almost the same. It's just an Euclidean algorithm, or it's just write it as a remainder and the quotient. Okay. So here, if we try to study the irreducible polynomial of well, in fx, then let's say K is a bigger set, it's a bigger field that contains the root of this irreducible polynomial. Then the ideal of all polynomials in fx at alpha is actually generated by fx. Well, which, well, more or less like you can try to find a map, which is a, well, evaluation map. This is a homomorphism, as we mentioned before, from fx to k. And then the kernel of this evaluation map is actually fx generated ideal. Okay, so which means, for instance, if you try to, well, let's make an easier example. If you try to find all the polynomials has a root 2, then what you want to find is actually all the polynomials that can be divided by x minus 2, right? Similar things here. If you want to find the polynomial ideal fx, then it's actually the same as you trying to find all the elements such that this element, if you evaluate it at say, for instance, fx equals to x squared minus 2, and your fx, your capital Fx, is actually qx. Then, if you try to study the ideal generated by this polynomial, it's actually the same as you trying to evaluate every polynomial now this is qx, and you map it to R, and here you try to evaluate this polynomial by substitute square root of 2. Then the kernel of this evaluation map is actually x squared minus 2. Which means if you have some polynomial such that you plug in square root of 2, you get 0, then this polynomial must be a multiple of x squared minus 2 on qx. Okay? Now this is a very interesting properties. We will see more. We will see more about this kind of irreducible polynomial and the ideal, this kind of relation. And if you are interested, you can try to study this field extension and splitting field of polynomial by yourself. Unfortunately, we don't have time to do that in our class. Any question? Any question?
Sorry, so what is evaluation of alpha?
Well, it's just this map maps a polynomial by to a number. This number is given by evaluate this this square root of 2. Okay. For instance, evaluation map. Evaluation map of square root of 2 evaluate something like x squared plus 1 is equals to, you plug in x to be square root of 2. Okay, which gives you 3. And this evaluation is actually a ring homomorphism, as we mentioned before when we discussed about the homomorphism. Okay, evaluation, plugging this operation is an homomorphism. Okay. Last thing I would like to mention before we have a break is, we mentioned this PID stuff, this ideal stuff. It is also useful for this kind of stuff, for this ideal stuff. It is also useful to check how far is a ring to a field. Sometimes a field has some better properties for us, so we want to see how far it is from a field to a ring. And here, there is a very interesting characteristic of rings, of a field, so that I think you may be able to use in the future. That is, well, if we have a field, then what can we say about the ideal of this field? What are the ideal of this field, of a field? Any suggestion? Because field is just a special type of ring. We know something about the ring. We know ideal is just some subset of a ring such that something happens. But if this commutative ring becomes a field, what can we say about the ideal? Well, the only ideal.
Oh, it's like it's the only ideal is the field itself because it has like units, like everything is a like unit and stuff.
That's right, because if you whatever ideal you have, right? Whatever ideal you have, well, it must contain one. Because you give me an ideal, I take one element from this ideal, then I can find the inverse on this f, then I multiply this element by this inverse. So that means, okay, this element times the inverse is in this ideal, so that means 1 is also in this ideal, right? The only ideals of this field are 0 ideal and unit ideal, which is 0 and 1. Okay. The interesting thing is, this is actually the equivalent condition of a ring becomes a field. If a ring has exactly 2 ideals, then R is a field. Okay. If you can see that some ring is actually has only 2 ideals, then what you can say is, okay, immediately this must be a field. This becomes a characteristic of field by ring, by the number of rings. Okay. Let me quickly prove it. The proof is actually easier than you thought. The first one, as I mentioned before, is trivial. Any ideal must contain 1, must contain everything if you have a field. So that's proof 2. Let's say, assume R is an ideal, well, it's a ring, has exactly 2 ideals. We know that 0 is an ideal, right? 1 is also an ideal for a ring. 0 is always an ideal and 1 is always an ideal. So it has 2 ideals. Does that mean that these are the only 2 ideals? Probably yes. But if you try to discuss, then you have to be careful because you list the 2 ideals and then you say that this is the exact 2 ideals that you have. Then you have to say that, okay, this 0 ideal is not equals to the 1 ideal on this ring. Otherwise, we may have a contradiction, right? Why 0 ideal is not the 1 ideal on this ring? Any idea?
The only case they are the same is the ring contains only 0 itself.
Yes, that's right. Then what is a contradiction?
In that case, there's only 1 ideal.
Great. So if 0 equals to 1, R only has 1 ideal. Okay. So we must have 0 not equals to 1 on this ring. So that means these 2 ideals are only 0 and 1. Okay. Then we want to show that this ring is actually a field. If you want to show that the ring is actually a field, well, the only thing you need to check is whether every element has an inverse or not, right? So I gave you A. If you want to show it is a field, I give you A, you must have an A inverse. How can we find A inverse?
Wait, what do you mean by how can we find A inverse?
Because if we want to show that this A, well, this R is a field, we only need to show that every element has an inverse, right? So now I gave you an element. The question is, how could we find it actually has an inverse? As long as we know that, we are done, right? Any idea how to find A inverse based on this condition?
Well, if like one it's only element, like it means that this set should have an inverse of A, because otherwise there is no way you can get an ideal generated by one if you only have A in the beginning.
I think you more or less guys get the idea. So if you have this A, then it has some relation with this ideal, right? But how can you find it? This is a problem, right? Let's consider this ideal. Okay? Consider this is an ideal. Right? This is an ideal of R. But we do know that you only have two ideals on this R, right? And this is not zero, so that means this must equals to 1. That means 1 is in this ideal. That means there exists B in R such that 1 is equals to B times A. Done. Okay. So you see, this is how we can use the property or the definition of ideal. Very important. Any question? Okay, so, well, I'll stop here and we will have 10 minutes break. We will resume at 27, okay? And I will try to pause and let's get started, okay? Okay. Let me remind you what we did last time, okay? We discussed about ideal and check how does this ideal can help us to understand the ring structure, right? It says that if you have a field, then the ideal structure of this ring or this field is quite simple. You only have two, right? This actually gives us a very interesting corollary. That is, well, if you have a field and R is a ring, okay, then every homomorphism from F to R is an injection. Okay, why is that? Can you imagine? Why is that true? What's the meaning of a map is an injection?
It means that we we don't get the same output from different inputs.
That's true. So how does it relate to this this field?
Because homomorphism has to map an identity to identity, right? But if we take, wait, no. Like we should just actually use inverses for sure, but I'm not quite sure how we do it.
Well, so how could we use our language we learned today to study an injection? To say a map is actually injected. How can we use our language? The ideal language, or something we've learned before. Like the injection, what can we say about the kernel of this map? What's the meaning of injection? An injection means, can you have something on your kernel?
Oh, it means that we have only one element in the kernel, right?
Which is 0, right? It must map 0 to 0, right? Nothing more than that. And this is actually an equivalent condition, right? You want an injection. You want phi A not equals to phi B. That means you want phi A minus phi B is not equals to 0. That means you want phi A minus B not equals to 0. Right? So injection for homomorphism is actually the same as you try to study the kernel. If the kernel is trivial, then your homomorphism is actually an injection. Okay? So now, why this kernel must be a trivial kernel? Or why this kernel must be a 0 ideal? Why is that?
Because if we have something else in the kernel, it cannot have an inverse.
Yeah, that's right. But that doesn't mean that, well, I just want to say that why every homomorphism must be an injection if you have this homomorphism from F to R.
Yeah, so it's like, so injection is equivalent to kernel having only one element, which is 0. So let's imagine that it's not an injection, that basically our kernel has something more than 0. Say it's an element A, then basically, but it's a field, so it should have an inverse. So if we multiply them together, we have, we cannot do
yes,
that.
your discussion is correct, actually. If you have more than one element on your kernel, there must be some contradiction, right? But if you have more than one element on this kernel, things becomes much easier. What is a kernel? A kernel is an ideal, right? Kernel is an ideal of your domain field. If you have a non-trivial element on this kernel, what does that mean? What does that mean? You have
The kernel is F itself.
Yes. Then that means the kernel must equals to everything, because you F only have 2 kernels for 2 ideals, either this one or everything, right? So that means phi is actually a zero map. But by your homework, you know that zero map is not a homomorphism as long as your R is not a zero ring. Right? Maybe I should say R is a non-zero ring. Then a contradiction. Okay. Any question? Okay. So you can see that if we discuss something about this kernel and ideal stuff, things will become much more complicated than you thought. And here, unfortunately, we're going to discuss more. And this more, this might be, the following part might be something very, very important in math, but it's very complicated, it's very confusing. So take care, okay? Now, let's discuss something since we mentioned that the ideal is what? The ideal is basically something that you want to use as an analog of this, something like 3z, something like this, right? So how could we study this 3z? How could we study this multiple, all the numbers as a multiple of 3, all the numbers of multiple of 8? This kind of thing. How can we study them when we try to study the integers? Well, we study this kind of set simply by studying this congruent, right? Mod 3 operation, right? Remember that? So that means, okay, if you have this modular operations of this kind of particular ideal, then maybe we can also try to study this modular operations on this general ideal, which is the definition of, modular and ideal. I gave you an ideal on a ring. We define the equivalent relation. Well, corresponding to this ideal. Okay, such that A, B in this in this R are equivalent if A minus B in R. Remember, this kind of relation is some mimic of this 3z, of this module, of this congruent operation, right? So of course we have to define it this way. And you will find that actually this is, this is an equivalent relation. This is an equivalent relation, and we have A, B, say A is congruent to B modulus I, and A prime congruent to B prime modulus I. Let's call it this way. Instead of 3, let's use I here. Means you have this kind of relation. Then we have A plus A prime is congruent to B plus B prime. Just like this congruent operation, and A times A prime is the same as B times B. which means this equivalent relation is actually will agree with the operations on your ring. Okay, you can do this addition, you can do this multiplication. Okay, and talking about this equivalent relation, one very important thing up here. I hope you still remember that. That is, whenever you have a set, you have an equivalent relation. We can do this set divide by this equivalent relation so that it consists of all the equivalent classes, right? As long as you have a set, you have an equivalent relation, you can do the quotient of this set and this equivalent relation. Okay, so here we can define the quotient of rings. Or the ring quotient by an ideal. Okay, that is, you use this equivalent relation, well, to divide your whole ring as an equivalent classes. Any question before we move on? Any question? Okay, so an interesting property is, well, you can do this kind of quotient, but, well, it doesn't mean anything. But then what you can see is, as long as you do this kind of quotient, some properties of your ring can be resumed, can be reserved. Okay, let's say R is a commutative ring, I is an ideal, then R modulus I, or R divide I, is a commutative ring. And the operations of this commutative ring, of this R divide I, is actually inherited from R. Okay? Or if you try to make it, well, if you try to write it in some other language, that is, you can use a projection map, pi, map from R to R divided by I, such that pi A becomes A plus I, which is the corresponding equivalent class to A. Okay, and this pi is a homomorphism. And this pi can give you, well, the natural way of defining the addition and the multiplication on this ring. The ring structure is actually can be induced by this pi, this projection map. Okay. Before we move on, any question? Because I'm going.
Just to understand, if I understand right, like the pi is kind of like rotating among the equivalent classes. Like if we have P0, it's like initial ideal, and then if we have P1, it's kind of like this ideal shifted by 1, and so that's how we obtain like all those equivalent classes.
You can think it that way, but I think an easier way to think about it is, how about we consider this AZ or 3Z? This is an ideal, right? Then what is Z mod 3Z? Well, Z mod 3Z, or this projection from Z to Z mod 3Z, is what? Is you map a number, say 100, to the equivalent class of 100. What is the equivalent class of 100?
It's just one, like
It's
modulo
just a
D.
one, because now what do you think about here? You try to think about the remainder of a number with 3, right? The remainder is 1. So which means this projection is basically you project this Z to Z3. Okay? The equivalent class of this Z modulo 3Z, the equivalent class, are only 3 things, right? Mod 3 equals to 0, mod 3 equals to 1, mod 3 equals to 2. Those are 3 equivalent class, right? Is that clear? So think about this example, okay? It's just like you try to take off everything that belongs to this 3Z. You try to take off everything that is a multiple of 3 from this number. What's left is something that can be seen as the class, the equivalent class that U belongs, right? That clear? Okay. Let me write a few remarks on it. First, well, the crucial part of this kind of quotient of rings, or of that proposition, of this proposition, is actually a commutative ring. This guy has a ring structure. The crucial part is you have to make the addition and the multiplication well defined. What do I mean by well defined here? Here, you must be careful, because now the well defined is something that really well defined. It's really something that important. Okay? What's the meaning of well defined? Because when you try to do this kind of operation, when you try to do this projection, then you can project 100 to 1. You can also project 100 to 4. The representative element could be different, right? Although they are in the same class, equivalent class, but the representative element will be different. So that means when you try to do the addition and the multiplication, you have to check this addition and multiplication does not rely on the representative element you choose.
Oh, so just to make sure, I think I asked this question before, but so what is like a definition of something being well defined? Like, is an algorithm to check that something is well defined?
Yeah, this is a very good point. So here is a very good example to say something is well defined or something is not well defined. For instance, if you try to define the addition of two elements on this R divided by I, then it is well defined, because if you have A in this R divided by I, B in this R divided by I, then A plus B is a fixed element in R divided by I. Okay, it is something fixed and is something unique. But for instance, if you define, well, on this z, r equals to z and I equals to 3z, then you can define the addition of 0 plus 1 is actually equals to 1. This means this addition is well defined. They do not depend on the representative element, because we can choose an arbitrary one. So 0 plus 1 is equals to 1. And 3 plus 1 is also equals to 1. Okay? So they give you the same element, final result. But something is not well defined as, for instance, you gave me an element, then, for instance, I ask, okay, I have a function defined on this element, which is the norm of this element. This map is not a well-defined map if you have this r in z and this I is 3z. Because if you try to evaluate, for instance, f1, then you should get 1. However, f1 is actually equals to f4, right? Then you get this same thing, it gives you 4. So which means you cannot determine the output from your input. Then this function is not a well-defined function. Which means in this particular examples, it means this function or this operation shouldn't depend on the representative element you choose. Okay? For instance, this operation, you map an element to the norm, depends on which representative element you choose. But this addition, it does not. Okay? So these two are different examples to say something is well-defined or not well-defined. Okay? That clear? And the second remark, this is remark 1. The second remark is, well, although we can say that R is a commutative ring, then R modular I is also a commutative ring, but something may not always be inherited. Some properties of this R and R divided by I may be different. For instance, like you may have a Z, right? Z is an integral domain. And you may have 6Z is an ideal. But Z mod 6Z is actually equals to Z6. It is not an integral domain, right? So which means originally you may have an integral domain, but eventually after you take this modulus, this quotient of rings, it may not be an integral domain. So be careful about this, okay? Any question? No? If no, then we have another proposition. As I mentioned before, if you have this pi, which is a projection map from R to R modulus I, then, well, you may have something very trivial. The kernel of pi is actually equals to I. Okay? So here, you can see why the kernel is very important. Because the kernel is more or less like this kind of I, right? Okay, which means this projection maps everything in I to 0. right? For sure, because this projection, it's well, the 0 here means this element by itself is in I. So of course, this projection has kernel I. Give you another example. So for instance, as we mentioned before, we have Qx. We can divide it by the ideal generated by x squared minus 2. Okay? And more or less, this kind of quotient operation is like something like you try to do this kind of operation such that you map all the polynomials here to, well, if the polynomial has a factor x squared minus 2, it maps to 0. Okay? Or if the polynomial has x squared, it maps to 2. Okay? You replace x squared by 2, which is why it should be somehow similar to this q square root of 2. Because you replace every x by square root of 2, right? It should be the same as this q square root of 2. This is how you understand it. This is how you understand this kind of operation. And this intuition is actually very important, which is something I'm going to discuss. This is so-called the first isomorphism, first fundamental theorem of isomorphism. Okay? Any question before we move on? The quotient operation of a ring. This is
Sorry, would you mind like repeating the statement you said about P out of R to equivalent classes of Ri? Because I think I kind of forgot it.
Well, that simply says that, okay, if on this element, you have something on this ID, you can take it out, right? If a number has some parts that is a multiplier of 3, a multiple of 3, then you can take it out, make it simpler. If you have a polynomial that it contains some part as x squared minus 2, it contains some part x squared minus 2, then you can use 0 to replace it, right? Like you have a polynomial like x squared minus 2 times x plus 1 plus x. This polynomial, if you try to do the projection, then that simply means it's it's modulus x squared minus 2. It's the same as x, right? So this polynomial is the same as x. Or we can use x 0 to replace x squared minus 2 on your polynomial. Yes, you can take off everything that contains x squared minus 2. Or you can take everything like x to be square root of 2. What left?
So that's why the kernel of P is I, because we're taking kind of like modulus I, right?
Exactly.
Oh, okay.
It has to be modular and ideal, not a subring. This is very important. Otherwise, it will not become an equivalent relation. Okay. So I'll move on. Okay. So you can see that here we kind of try to say this and this, they should have the same structure. And how could we define this same structure rigorously? This is something we have done before, which is so-called the isomorphism. I hope you still remember that. I hope you still remember this term. Other than homomorphism, we have so-called isomorphism. What is an isomorphism? Isomorphism means it is a map, it's a homomorphism. Meanwhile, it's a bijection. It's a one-to-one correspondence, right? So we have one here and one element on this ring and another element on this ring. They are corresponding, one-on-one correspondence. Okay, so this is a method we can try to say two rings are actually the same. This is how we say two rings have the same structure. To remind you, let me give you some examples. Okay, for instance, if we try to consider this Z6, all the equivalent class module 6, and we try to consider Z2 cross Z3, which is all the pairs A, B, such that A is in Z2 and B is in Z3. Okay, and these two are actually the same. We can find the map from the homomorphism from Z6 to Z2 cross Z3. By doing what? By doing phi x is actually equals to, you module 2 first and module 3. Okay.
Oh, this is a bijection because we have Chinese.
This is this is actually a bijection, and this is actually it's actually a homomorphism. Okay. By the way, so as you mentioned, there is something about this kind of thing, so-called the Chinese remainder theorem. This is something that is pretty interesting, and you have a general description using the language of ideal. However, we don't have enough time, and I don't want to confuse you, so I will not discuss that. Okay. But basically, you can see that this phi is a bijection, and this phi is actually a homomorphism. So that means Z6 and Z2 cross Z3, they are actually the same. It's isomorphic to Z2 cross Z3. We use this notation, means isomorphic to this one, or they are the same. Okay, it's equal with a tutor on top. And of course, you cannot always be as lucky as this one. For instance, if you try to study Z4 and Z2 cross Z2, you may find Z4 and Z2 cross Z2, they are not isomorphic. Why is that?
Because Chinese remainder theorem states that we have to have them like co-prime.
Well, but it doesn't say that. Well, if they are not co-prime, then something is not true, right?
Oh, really?
No, it doesn't say that, at least. Although it might be true, but it doesn't say that. You cannot quote the Chinese remainder theorem and then say this is not true. Okay? Well, the reason why these two are not equivalent and are not isomorphic to each other is simply because a very interesting trick here. You try to check the number of zero divisors both sides. Because you know that if they are isomorphic, then of course they should have the same number of zero divisors. Otherwise, they cannot have the same structure, right? So if you check the zero divisor, the only zero divisor on Z4 is 2. But the zero divisor on Z2 cross Z2 are 1, 0 and 0, 1. These two multiplied together equals to 0. Okay, so you have 1 zero divisor here and 2 zero divisor here, so they are not the same. Okay. Well, this is just a refreshment for you. Okay, just let you to remember how we can say about the isomorphism. And now let's discuss the general theorem about how we can check two rings are isomorphic to each other. Okay, this is something very important, and this is something very how could I say, very abstract. Okay. Let me state so-called the first isomorphism theorem. Which is, well, the most useful tool to help you, most powerful tool to help you to prove two rings are isomorphic. Okay, let's say we have an R and S be commutative. And suppose phi from R to S is a ring homomorphism. Meanwhile, it's an onto map. What's the meaning of onto? That means it's a surjection. Okay, it can travel all over S. Then what we can say is, if you use R, modulus the kernel of phi, which is an ideal, it's isomorphic to S. Okay. Or on the other notation, another notation, you may have an isomorphism from R to S. Okay. On the other hand, you can use a projection map pi from R to R modulus the kernel of phi. Then the claim is you will have a canonical phi induced by this phi and pi, such that this and this, they are actually will give you an isomorphic. This graph is actually, you can go from here to here, or you can go from here to here. It's a so-called a commutative graph or commutative diagram. Or it means that phi, this map phi is actually equals to phi bar composed with pi. Okay? Any question before we move on, before we prove this theorem?
Yeah, can you please give an example?
Of course. For instance, like QX, okay? Our homomorphism is a evaluation map or substitution map, such that you substitute x to square root of 2. Then this is a homomorphism from Qx to Q square root of 2. Right? It's just a plug in. You plug in every polynomial by x by square root of 2. Then, as we mentioned before, what is a kernel of the evaluation map of square root of 2 on this Qx? Well, the kernel is what?
It's x squared minus 2.
It's x squared minus 2, right? So from this isomorphism theorem, we know that Qx modular x squared minus 2 is the same as Q square root of 2. Okay? This is a very good example. Okay? Any question? Any other question? We have more examples and you will see. After I prove it, I will show you a very, very interesting example. Much better than this one. Any question?
Oh yeah, wait. Here the Q square root 2 is, do you denote like the numbers like a plus b square root 2? Or
yes,
do you denote
a plus b times square root of 2, exactly. Or you can also write it as, okay, a polynomial that replaces x by square root of 2. which always have the form a plus b times square root of 2, right? They are the same. They are the same. So which means, well, q square root of 2 is equals to all the polynomials. You plug in square root of 2. And it's actually equals to a plus b times square root of 2, a, b in q. Right? They are the same. That clear?
So the last statement is true because we know that qx divided by x squared minus 2 should have a degree that's less than 2. And so basically, if we just plug in the square root of 2 into any polynomial,
In
we'll
this
get
equation, are you
like
seeing this equation, right?
no, like the statement that we got because of the theorem.
one?
Yeah, I'm just trying to see why it is intuitively true.
This is true because you have this evaluation map, maps x to square root of 2. This is a surjection, right? And you know that the kernel of this one is actually equals to this, well, everything that can divide x squared minus 2. Okay? Then, by the first of isomorphism theorem, we know that these two are the same. Okay? This is an application of the first isomorphism theorem. That clear? That clear?
Yeah.
Okay. So we have this. By the way, this is actually, if you try to check your textbooks, then it is a best, well, it is also a good way for you to show that this q square root of 2 is actually a field. Instead of a ring, it's actually a field. It's simply because this right-hand side or this left-hand side is a field. Why this left-hand side is a field? Because you divide this principal ideal, and this is a irreducible polynomial, and as long as you have a fx divided by a irreducible polynomial induced principal ideal, then you will have a field. Okay, you can check on your textbook if you are interested. This is a biproduct. Say that this is actually a field. Q square root of 2 is a field. Okay, so now let's try to prove this here. The first isomorphism theorem. Yeah, maybe I will leave it here. I'll leave it here so that you can see. Okay, so how can we prove this first isomorphism theorem? Well, the proof is actually not so hard, because as long as you know what to prove, then you can prove it. Okay, so let's say if you have A and B, they are in the same class. Then we know that phi A is, well, minus phi B is equals to phi A minus B is equals to, since A is congruent to B, that means A minus B are in this ideal, it's in this kernel, so it's 0. Right? So that means phi A equals to phi B. So that means there exists a well-defined function. And this function the value of this function does not depend on the representative element you choose. There exists some element phi bar, well, some homomorphism phi bar from R modular kernel of phi to S. And the phi bar, A bar, we can simply evaluate at phi A. Okay, and A bar is an element in this R modulus kernel of phi. So you can check that phi bar is a homomorphism. And moreover, this phi bar is an onto, which means it's a surjection. This is also easy to check because phi is a surjective, Then of course phi bar is also a surjection. Because well, whatever value you take from phi, you'll get the same value. You'll get the similar value of phi bar, the same value of phi bar, whatever you have.
Oh, sorry, I'm kind of confused. So phi bar, A bar is equals to phi A. Like, where would we get that from?
Well, we define this phi bar. We define this phi bar. It defined on this R modular kernel of phi. It defined on this equivalent classes, such that you gave me an equivalent classes. I define this value of this function to be phi at this equivalent classes representative element. And you can see that it doesn't, well, the value of this phi bar doesn't depend on what element, what representative element you gave me. So,
but why does it depend on the represent? Like, say if we have like A bar is equals to B bar, right? But then phi bar of A bar would be equal to phi A, but phi
yes.
bar from B bar would be equal to phi B.
Yes,
so,
that's right.
But
But
they
you
are
find
equal.
phi A equals to phi B, right? Because of this. So which is why it doesn't depend on, well, which representative element you choose. This function, this homomorphism is a well-defined homomorphism. Okay? So, and you can say that phi bar is also an onto, right? Whatever value you have here on phi, you will have the corresponding phi bar as this value. Then the only thing is you need to show it is a injection, right? Well, how it is an injection, you have to consider this kernel of phi bar. What is a kernel of phi bar? Well, the kernel of phi bar is actually equals to 0. Right? If you want to have 0, here, then this A must be on your kernel of phi, which means they are in the same equivalent class as 0. So that means, okay, phi is a bijection. And phi is a homomorphism, and it's a bijection, so that means R modular kernel phi is isomorphic to S. Okay? Any question?
Why is it onto?
Why is it onto? So for any element on S, right, there exists some A such that, well, for any element B on S, there exists, let's say, small s on S, there exists some A tilde on R such that phi A tilde equals to S, because phi is onto, right? Then phi bar A tilde, the equivalent class of A tilde, gives you phi A tilde, gives you S. So for any element in S, you have the corresponding pre-image, at least one. Okay, which is why it's onto. Any other question? Okay. So this is a very, very important theorem. It can tell you, for instance, as we showed before, some ring isomorphism. Okay, this is equivalent to this one. And of course, there are something more. There are more examples about application of this homomorphism theorem, well, isomorphism theorem. For instance, let me give you a complicated one. For instance, I can prove that Zi modulus 1 plus 3i, this ideal, is isomorphic to Z10. This is something not so clear, I believe. Z10 is, well, it's something only contains Z. But on the right-hand side, you have a lot of things. It's actually on the complex number. It includes some complex number. Then, how can we use the fundamental theorem? Well, the first isomorphism theorem to prove these two rings, they are equivalent. Let me show you how. Okay. So the idea here, or the intuition here is, what's the meaning of Zi modulus 1 plus 3i? Well, that simply means on this Zi, after you modulus it, you want 1 plus 3i equals to 0. Okay, this is what you want. 1 plus 3i is the same as 0 after you take this modulus. What does that mean? That means 1 is equals to minus 3i. Right? That means what you want is you multiply I both sides, I equals to 3. And that means if you take square both sides, you have minus 1 is equals to 9. That means 10 is equals to 0. Which is why you should guess this Z10 is, well, it's the same as the left-hand side. 10 is equals to 0. Sorry. All right. So this is how you make this Zi somehow looks like Z10. But of course, this is not a proof. This is just an idea about how you can imagine why the right-hand side is the left-hand side. They are the same. Okay. Let me try to prove it. If you want to prove it, you want to build the homomorphism and then try to make it a surjection, then try to make something like this guy to be the kernel. Or the other way. Let's consider this map from Z to Zi modulus 1 plus 3i. Okay, let's consider this one. And this is a ring homomorphism. If you want it to be a ring homomorphism mapped from Z to another ring, what do you want? There is a, well, I hope you still remember this. If you want a homomorphism from Z to an arbitrary ring, then this phi is unique. It's somehow unique. This is a theorem or a proposition that we mentioned a long, long time ago when we talked about the homomorphism, right? How can you define this phi? How can you find a nature homomorphism from Z to R? Pretty easy. You define phi to be mapped from 0 to 0, mapped from 1 to the identity here, and then you map from Ni, well, N, you map from N to N times the identity on this R, which is identity plus identity plus identity plus N identity, right? So, which means If you do want to find the homomorphism from Z to this ring, then it's actually unique. It must map this 0 to the 0 element here, must map from Z1 to 1 element here. Okay? So, well, what's the right hand side? What's the right hand side then? Zi is actually equals to A plus Bi, where A, B in. Okay? And Zi modulus 1 plus 3I is what? It's actually you, as we mentioned before, you replace this I by 3, which means you map, well, it's actually equals to A, B in C, the equivalent class of A plus Bi, but we do know that it's also, well, another representative element of A plus Bi is A plus 3B. You can replace the I to be 3. And it doesn't change this equivalent class. Okay? Ah, that's very interesting, right? Then what you do have is you can map a number Z to this the corresponding equivalent class to this A plus 3. Right? Which is for an n in this well, first you can see that then all the representative elements here, this phi, will map n to the n class, the equivalent class of n, which is well, if you write it this way, then it's actually something here, right? This is a phi will work. Phi will map n to the equivalent class corresponding to n. Then the thing is, then you find that phi is actually onto, because as long as you cover every integers here, you can cover every element on this ring. Okay, so first phi is onto. Then the next thing is we need to find the kernel of phi. What is a kernel of phi? So what is a kernel of phi? Suppose n belongs to this kernel of phi. Then that means phi maps n to the equivalent class of n. It must be the same as 0, right? So it is the same as the equivalent class of 0. So that means, well, this n's equivalent class must be able to written as some complex number times 1 plus 3. Otherwise, it cannot be the same as the equivalent class of 0. Right? So that is A minus 3B plus 3A plus B. And we know that this n is in Z. So that means if you want this n to be on the kernel of V, you must have 3A plus B equals to 0. Or B equals to minus 3A. Right? So that means if n is on the kernel of phi, we must have n can be written as A minus 3B, well, A minus 3A times I times 1 plus 3I, which is A times 1 minus 3I times 1 plus 3I. 10. Right? So n is in Z. N divides 10. Right?
Wait.
Mhm.
I don't know. I'm a bit confused.
Okay,
Well,
so let me explain it again so that it might be, well, or you may ask me. Well. So basically, this phi, it must map n to the equivalent class of n on this set. And on this set, it has a nature equivalent class. It can be written in this way, right? So which means, well, you must use phi to map n to the equivalent class of n. And now what you want to find is a kernel of phi. As long as you have the kernel of phi, then we know that phi divide, quotient, phi modulus kernel of phi is actually equals to this one. Z modulus kernel of phi is actually equals to this one, right? So you want to find what elements are in the kernel of n of this phi. So you try to say, okay, you take this projection, phi n, it will map to this equivalent class of n. Then that means it's the same as 0 on this ring, right? What is a 0 on this ring? 0 on this ring means it must be a multiple of 1 plus 3i, or it must be in this in this ideal. So which means n must be written in this way. So which means n must be written in this way.
And then we just plug in b equals to minus 3a, and then we just open the brackets, and we, oh, okay.
Yes, then we find that n must have the form 10 times a. So that means the kernel of phi is a subset of Z10. Well, I mean 10Z, I'm sorry.
And then we'll just have to prove another side, right?
Yes, we have to prove another side, but we know that this is an ideal. So as long as we can prove that 10 is in this kernel, we are done, right? Because 10Z is the smallest ideal that contains 10. So does 10 in this kernel? Yes.
Oh, yeah, because it's just simply 1 minus 3i multiplied by 1 plus 3i.
It's just a 1 minus 3i times 1 plus 3i. It's equivalent class is 0. Right? So nothing more. So that means kernel of phi is equals to this 10. That means by the first isomorphism theorem, Z mod 10Z is isomorphic to Zi modulus 1 plus 3i. Okay? Any question?
No questions, but that was cool.
Well, this is one application of this isomorphism. First isomorphism theorem. There are a lot more. There are a lot more applications of it. You may see that. I may mention some of them. Well, I may mention, since we have the first isomorphism theorem, I may mention the second isomorphism theorem and third isomorphism theorem later on Thursday. But right until here, right until this first isomorphism theorem, will be on the test. Okay, the second and the third isomorphism theorem. Well, I think the second and third isomorphism theorem, I will also mention that a lot on Thursday, and we will have the exam after Thursday's class. So it will also on the exam, but will not be very hard. Okay. So I will stop here, and you guys can try to check the first, second, and third isomorphism by yourself, and then on Thursday we will resume and discuss more about that. And then after the class, I think at 7 p.m. we will have our midterm. Okay, our midterm will about everything about the ring. Okay.
So midterm from 7 p.m. to 7 a.m. on
7
Friday?
p.m. to 7 p.m., 24 hours.
Ooh, nice. Okay.
And yeah, so then that's all for today. I will upload everything I wrote and later. And I think now is my office hour. If you have any question, you can ask. And if not, you can just feel free to go. I will stop recording now.